Good day, class. Sir Reve is back with his new topics for week 7, Exponential Equations. So for this topic, we will have 4 sections to explore. First is the definition of an exponential equation. Then we have to review some related topics, such as the laws of exponents, laws of logarithms, and the one-to-one property of exponential functions. Then we have to deal with solving of exponential equations, which will use different methods that are applicable to different equation cases. Lastly, we have to discuss the real-life applications of exponential equations through exponential growth and decay. Without further ado, let's begin. What is an exponential equation? So, equations involving exponential functions, sometimes referred to as exponential equations, are expressions in which the value of the variable, say x, satisfies a given statement. For example, we have 4 raised to x is equal to 13, and 1/5 raised to x plus 2 is equal to 15,625 raised to 2x minus 7. So how does it differ from an exponential function? An exponential function shows the relationship between two different variables, such as, or for example, we have y is equal to 2 raised to x plus 3. Basically, there are two variables involved in an exponential function, and there is no need to solve for the value of x. That's why exponential equation is not the same as exponential function. Next, let's have a review about the law of exponents, law of logarithms, and the one-to-one property of exponential function. We have the following laws of exponents: the law of product of power, law of quotient of powers, law of power of power, law of power of product, law of power of quotient, law of negative exponent, and law of zero exponent. But for our lesson for today, one of the most, or three of the most important laws of exponents are the law of power, the law of negative exponent, and sometimes the law of zero exponent. Next, we have the laws of logarithms, which includes the logarithm of a product, the logarithm of a quotient, the logarithm of a power, the logarithm of one, the logarithm of the same number as a space, and the inverse property of natural logarithms. So the logarithm of 1 and the logarithm of the same number as base are two of the topics that I have mentioned during our lesson about logarithmic functions. While this inverse property of natural logarithms simply state that the natural logarithm of the constant e raised to x is just simply equal to x. We also have this one-to-one property of exponential functions. Recall that in f of x equals b raised to x, if fx sub 1 is not equal to x sub 2, then b raised to x sub 1 is not equal to b raised to x sub 2. Conversely, if b raised to x sub 1 is equal to b raised to x sub 2, then x sub 1 is equal to x sub 2. What it simply states is that whenever the base of two exponential expressions are the same, then their exponents can be equated. Okay? Now, let's proceed to solving exponential equations, wherein, in most cases, the main goal for exponential equation is to express both sides as the power of the same base. But this is just one of the cases that we will be tackling for today's lesson. Specifically, this is what highlighted in the method 1. The case is both sides of the equation can be expressed as the power of the same base. Example 1.1. Find x if 7 raised to x is equal to 343. We know, class, that 343 can be expressed as the power of 7. Specifically, it is 7 cubed, right? So, since 343 can be transformed into its exponential form, which is 7 raised to 3, we can easily apply the one-to-one property of exponential function, since both sides of the equation are now expressed as the power of the same base, which is 7. From that, we can conclude that x is equal to 3. Therefore, our solution set is the set containing 3. The first example is quite easy for you. Let's complicate things a little. Next example, we have this problem. Solve for x into raised to 4 x plus 1 is equal to 512. Again, class, 512 can be expressed as the power of 2. Specifically, it's 2 raised to 9. So both sides now are expressed as the power of the same base, that is 2. And we know that whenever this case is visible to us, we can apply the one-to-one property of exponential function. Since they have the same base, we can simply equate their exponents. So 4x plus 1 is equal to 9. We can simplify the equation by adding negative 1 to both sides, giving us 4x is equal to 8. Then we can multiply both sides of the equation by 1/4, giving us x is equal to 2, which is the element of our solution set. Next example. What is x in 27 raised to 1 minus x is equals to 9 raised to x? So we know, class, that we can notice that neither of the sides can be expressed as the power of either of the bases of this equation, right? So 27 cannot be expressed as the power of 9, and 9 cannot be expressed as the power of 27. But we know that 27 can be expressed as 3 cubed, while 9 can also be expressed as the power of 3, which is 3 squared. That could be possible because both sides of the equations can still be expressed as the power of the same base. From that, we will have 3 cubed raised to 1 minus x is equal to 3 squared raised to x. Applying the one-to-one property of exponential function, we can have this value. But before that, we have to also apply the law of power of a power. That's one of the laws of exponents that I highlighted earlier, by which we have to multiply the exponent 3 and 1 minus x, giving us 3 minus 3x. And in the right side of the equation, we have to multiply 2 and x, giving us 2x. Now we will have 3 minus 3x is equal to 2x. Simplifying the equation, by combining similar terms, we will have negative 5x is equal to negative 3. And dividing both sides by negative 5, we will obtain x is equal to 3 over 5. Therefore, our solution set is the set containing 3 over 5. For our last example, for method 1, we have to solve for x in 5 raised to x times x minus 6 is equal to 1 over 25 raised to 4. So the first step, class, here is still the same. Express both sides of the equation as the power of the same base. So we know that 1 over 25 can be expressed as 1 over 5 squared, right? But to move 5 squared to the numerator, we have to apply the law of negative exponent. So we have 5 raised to x times x minus 6 is equal to 5 raised to negative 2 raised to 4. Moving forward, applying the law of power of a power in the right side of the equation, we will have 5 raised to negative 8. And now, since both sides of the equation are expressed as the power of the same base, we can apply the one-to-one property of the exponential function. We can obtain x times x minus 6 is equal to negative 8. Simplifying it would yield to x squared minus 6x plus 8 is equal to 0, which is a quadratic trinomial. And in a quadratic trinomial, we know that it can be factored. Specifically for this, we have x minus 4 times x minus 2, which when equated to 0 will yield to value of 4 and 2. That's why our solution set for this is the set containing 2 and 4.